All right, Geology 105 Physical Geology students, this is Dr. Mark Tinsley, and we are going to be looking at streams. Now, the streams lecture was supposed to take us over 2 weeks. We were going to do 1 week on streams, 1 week on groundwater. But because of all the to-do around the coronavirus and our remote learning environment now, I am going to do the streams and groundwater lecture this week. And so we're going to do it both. And we're going to have a lab related to streams. It's going to be pretty cool. I hope you enjoy it. I want to say, though, make sure you're staying up with the stuff that we're doing in this class, because I know a few people have fallen behind. I don't want anyone to fall behind. I want you all to stay up on what we're doing. So hang in there, be diligent, do your work. You know how I am. Come on, y'all know me. I'm very reasonable, and we're going to get through this together. But I need you to do your work, and if you can do that, you're going to be all right. All right. Without, as they say, further ado, let's jump in. Streams. All right, so let's talk about the distribution of the Earth's water. The ocean covers about 71% of the Earth's surface. Most of you knew that already, and contains roughly 97% of the Earth's water. So the oceans they cover over 70% of the Earth's surface and contain roughly 97% of the Earth's water, right? 60% of the northern hemisphere is covered with water. 80% of the southern hemisphere is covered by water. You can see this if you look at the globe from the North Pole. You see more land than if you look at the globe from the South Pole. So more water in the southern hemisphere than in the northern hemisphere, but the globe is covered by over 70% water. So we are a water planet. And that ocean water is salt water. So it means 97% of the Earth's water is non-potable. We can't drink it. So if 97% of the Earth's water is salt water, fresh water is only about 3% of the Earth's water. And that's obviously contained in lakes, rivers, ice and snow, groundwater, gas in the atmosphere, and as water inside of biological organisms, including you and me. So here's just a visual representation of that. You can see the green block on the left shows about 97% ocean water is saline, leaving that little sliver of blue at the top as fresh water. And you break that fresh water down in, you see most of the water, 68.7% of fresh water, is in glaciers and ice caps. Isn't that crazy? Only 30% in groundwater, and surface water only accounts for 1.2% of that fresh water. Break that surface water down, and you can see that ground ice and permafrost contains almost 70% of that water. Lakes are only 20% of that 1.2%, which is the 2.5%. You see how it goes. In other words, freshwater lakes and streams and stuff are only a tiny fraction of the water at the surface of the Earth. Most people don't realize that. When we talk about water in the Earth, we need to talk about the hydrologic cycle, or the water cycle, as some people call it. This is a continuous exchange of water between the ocean's atmosphere and land. Just like we have a carbon cycle, nitrogen cycles, rock cycles, we also have a water cycle. This cycle is driven by solar energy and gravity. In other words, solar energy evaporates water. Gravity causes precipitation to fall. The sun heats here's how a typical cycle goes. The sun heats the ocean water. Evaporation occurs at the ocean surface. So water goes into the air. The wind transports this gaseous water around the globe. Precipitation occurs. The water falls back to the earth at some place. Snow, rain, that type of thing. Gravity then transports that water downstream via streams, glaciers, and groundwater, eventually bringing it back to the ocean. So most water, but most water returns directly to the ocean. What that bullet means is that most of the time precipitation or evaporation occurs, and then precipitation occurs right back into the ocean. So a lot of times that cycle is completed very, very quickly. 70% of water that falls on land immediately returns to the atmosphere via evaporation. That's crazy. Most people don't realize that. So when water falls on the Earth, most of it immediately evaporates back into the atmosphere and through transpiration in plants. That means 30% of the water that falls on land remains in lakes, streams, and a lot of it goes into groundwater. But all of that typically returns eventually back to the ocean. Lakes go into streams, streams go into the ocean, right? Groundwater goes into streams, streams go into the ocean. So It may take a long time, but the hydrologic or water cycle is completed, ocean to ocean, over time. This is an idealized look at the water cycle, so you can see that. You see the evaporation and condensation, you see the sublimation, you see the precipitation, you see the groundwater. It's all right there. Let's talk about rivers and streams for a minute. As we said, it's only a fraction, right? Only about 0.004%. So that's small. 0.004% of freshwater is in streams or rivers. But this water obviously is very important to us, so we want to talk about it. Some terms when it comes to rivers and streams, we oftentimes talk about the head or the headwaters of a stream. That's the source of the stream, where the stream starts. A tributary is a stream or river that flows into another stream or river. So the one that's flowing into, we call a tributary. The one that's flowing into another is called the tributary. A drainage basin or area is the area drained by a stream or river. Every stream or river drains area, a land area, and that land area is called the drainage basin. And a divide is an elevated area separating two drainage basins. Okay, and you can read more about that and see some diagrams, hopefully, in your textbook as far as that goes. I'm not going to stick on this point very long, because we've got to keep going. Let's talk about drainage patterns, how streams drain the land. There's several different types. We're going to look at 6. Dendritic, rectangular, trellis, radial, annular, and parallel. I'm going to go through these real quick and describe them, and then we'll look at pictures, okay? So the dendritic pattern is a pattern that looks like veins on a leaf. When we see this kind of a pattern, it means that the underlying rocks are usually flat-lying rocks, not tilted rocks, but flat-lying, and they're relatively uniform. The rectangular drainage pattern, you'll see sharp 90-degree bends in the river, and this is where the underlying rocks are jointed or fractured, so the streams are following those joints or fractures. Trellis drainage pattern looks like a garden trellis or a grapevine trellis. Usually when we see this, the underlying rocks are folded into valleys and ridges, like in the Shenandoah Valley of Virginia. The radial pattern, where the rivers flow from a central point, usually a hill, like the spokes on a wheel. An annular pattern is where the flow is around a central point, so it's almost like concentric circles. And then a parallel pattern is where the streams and rivers run parallel to one another. This usually means the underlying rocks have a uniform slope, uniform character over a large area. So if we want to look at these patterns more in visual form, you can see them here. There's the 2 at the bottom, multi-basinal and contorted, we're not going to learn. But the top 6, we are going to learn. So you see dendritic there, look like veins on a leaf. Parallel, they're kind of parallel to one another. Trellis, right? You can see the pattern there. Rectangular, the 90-degree bends. Radial, from a central point. And then annular, concentric circles. So I hope you can see those. They're pretty standard drainage patterns. And you will need to know these 6, okay? So, again, descriptions here, visual there, and, of course, your book talks about these as well. When we talk about stream discharge, and I realize I'm going through this fast, but, again, there's no need to belabor the point, right? So if you have questions, please reach out to me and let me know. All right. So stream discharge. Discharge is the volume of water passing a certain point in a given time frame. We usually express discharge in cubic feet per second, or sometimes you'll see cubic meters per second. But here in the United States, we're oftentimes cubic feet per second. Discharge is a function of the stream's cross-sectional area and velocity. In fact, the equation for discharge is discharge equals the cross-sectional area of the stream times its velocity. And if cubic feet per second, you can see how this would work. Area is in feet squared, right? Velocity is in feet per second. So if you multiply feet per second times feet squared, you get cubic feet per second, right? So what affects velocity of a stream? The gradient, in other words, the slope of the stream. The higher the gradient, the higher the slope, the higher the velocity. That stands to reason, right? The volume of water affects the velocity of a stream. as the volume of your stream goes up, the velocity typically goes up. We've all seen this when a flood stage of a river, like if the James River floods. If you've ever seen the James River flooding around here, which if you've lived here any time, you have seen that, you notice that the stream's velocity picks up, doesn't it? And then the texture of the stream channel. In other words, if the bottom of the stream channel is very rough in texture, it's going to slow the velocity down. If it's very smooth in texture, it's going to speed it up. Typically, the gradient of a stream decreases from the headwaters of the mouth to the mouth of the river. So at the headwaters of a stream, you typically get the steepest gradients. And then at the mouth of the river, you typically get the shallowest gradients, which most people think, well, then that must mean the velocity decreases as you go downstream. Well, in fact, no, the velocity typically increases or can increase from the headwaters to the mouth, and that increases because the increased in volume. As you go downstream, you typically get more and more volume of water. So sometimes the volume can become so massive that the velocity actually picks up as you go downstream. But generally, highest velocities are near the headwater and lowest near the mouth. Okay. This is just a diagram showing you the cross-sectional area of a stream, width times depth, and the velocity. And you can see the equation there for discharge area times velocity. So this is just a graphic representation of the last slide. When we talk about stream gradient, we're talking about rise over run. We talked about this in lab one time. Change in elevation over the change in horizontal distance, usually again in feet per, slope is in feet per mile typically, right? And the higher the slope, the greater the velocity typically. This is a stream gradient profile. It's from the headwaters on the left, or the source, to the mouth of the river on the right. You can see that generally, this is just, again, a graphic representation of a previous slide. That as you go downstream, the further you get from the source, the closer you get to the mouth, the shallower, typically, the stream gradient becomes. All right, when we look at the flow of a river and we look at flow dynamics, typically, there are two types of flow that exist, laminar and turbulent flow. Laminar flow is when the molecules of water are flowing parallel to one another and not a lot of friction between them, not a lot of bumping into one another, and then forces, are primarily horizontal. Turbulent flow, however, is when the molecules of water follow a chaotic pattern. They're bumping into each other, going all over the place, and you've got horizontal and vertical forces at play. It's the parallel forces, the horizontal forces, that transport sediments downstream. It's the vertical forces that pick up and erode sediment from riverbeds. So you need turbulent flow for erosion to occur. Here's a graphic representation of laminar flow on the left. Everything's kind of smooth and parallel and horizontal. In turbulent flow, everything's everywhere. As you can imagine, if I'm going to pick something up off the stream bed, then I've got to have turbulent flow. I got to get down there and kind of scoop it up, right? But it's that component of laminar flow, because most streams have both laminar and turbulent flow. It's that component of laminar flow that moves things downstream. When we talk about erosion of material in a stream, velocity is the primary driver of erosion. As a stream's velocity increases, erosion potential increases. So I can erode more as my stream moves faster. And we know this, right? Because what do you do with your garden hose if you want to wash the mud off the sidewalk, right? You spray it harder, right? You put your thumb over the end of the nozzle so that the water comes out faster so you can spray it. Why do you do that? Because you're trying to increase the velocity of that water so it hits those soil particles on the walkway and pushes them off, right? Because larger materials require more velocity to erode. Interestingly, as I put in here, extremely small particles like clay require high velocity to erode as well because of the cohesive forces in the clays. So clays will oftentimes, even though they're very small particles, they take a lot to erode because they stick together so well. So very small particles and very large particles require high velocity to move, but sand-sized particles are usually the easiest to erode. Okay. Streams erode. They erode by down cutting. So a stream cuts down vertically into the ground over time. And That down cutting doesn't go on indefinitely. It stops at base level. And the easiest way to explain base level is that base level is the lowest level a stream can flow. The ultimate base level is the ocean. In other words, a stream can't cut down lower than the level of the ocean. It makes sense, right? Because if it did, then it would have to flow upstream to get to the ocean. Can't do that. So it's not going to cut down any lower than the level of the ocean. And most streams that don't flow into the ocean, they have what we call a local base level, which could be a lake or another large body of water that it can't cut lower than. Think about it. A mountain stream coming out of the mountains into a mountain lake, that stream's not going to cut lower than the mountain lake, because if it did, again, it would have to flow upstream to get to the lake. Water doesn't flow upstream. I think you get the point. This is a Hjulstrom's diagram. This shows you what I said in the last slide about velocity versus particle size. As you can see here, very small particles on the left-hand side of the scale on the x-axis take a lot of velocity to erode, and very large particles on the right-hand side take a lot of velocity to erode. But the sand-sized particles in the middle there, in 0.1 millimeter to 1 millimeter, they take the least amount of energy. Right? Okay. This is just a graphic representation of base level. The dam there creating a lake or a reservoir, that is a local base level. So the streams to the left of that dam would not cut lower than the top of the reservoir, right? So that's a local base level. When we talk about stream transportation, we talk about things called competence and capacity. Competence is the largest particle a stream can carry at its velocity. So at a certain velocity, a stream has a certain competence. It can't carry particles larger than a certain amount. Increase the velocity, the competence will go up, right? As will typically capacity, which is the total amount of sediment a stream can carry. Again, as velocity goes up, competence and capacity go up as well, which is the third bullet. Competence and capacity are a function of velocity. That is, velocity decrease equals decrease in competence and capacity, or velocity increase equals an increase in competence or capacity. Faster water can carry bigger and more particles, in other words. When we talk about load, I know it's a lot of terminology here, but when we talk about load, we're talking about the material a stream carries. There's 3 types of load. We talk about in geology, we talk about suspended load, bed load, and dissolved load, and they're very easy to differentiate. Suspended load is that load that is that material, sediment that's carried in suspension, clays, silts, small particles. And in fact, in any stream, about 70% of what's being carried is carried in suspended load. It's suspended. It's up in the water being carried along. Bed load is larger particles that are usually pushed or bounced along the bottom of the stream bed. Sand-sized particles and larger are typically in your bed load. The bouncing motion as a particle bounces along the bottom as it's moved downstream is called saltation. And about 10% of the material in a stream is moved in bed load. That leaves about 20% as dissolved load, which is just material that's dissolved in the water. Okay. All right. So there's saltation, particles bouncing along the bottom. And that's part of bed load, right? Okay, so what do streams do geologically? Well, they work to level the land. Streams erode and streams deposit. They erode upstream typically and deposit downstream. And you can imagine if I'm upstream in the mountains and I'm eroding, and I'm downstream in the valleys and I'm depositing, over time, right, I am going to theoretically level the land. So look at this diagram here. Top diagram you see that's our starting point. And then as we erode the hilltop on the left and deposit in the valley on the right, look at how we over time level the land. And this is what streams do for us, okay? Let's talk about the life of a stream. And again, I know we're going through this quickly, but just hang in there, all right? Life of a stream, basically streams start off just like we do as youthful. So you have youthful streams. These are usually found near the headwaters or the head of a stream. As you can imagine, there are primarily erosional forces at play in a youthful stream or a stream found near the headwaters, where gradient and velocity are at a maximum. Youthful streams are typically V-shaped in cross-sectional area, and they downcut, and they provide primarily erosional energy and mass wasting driven by gravity. And we haven't talked about mass wasting yet, so we'll talk about that, I think, next week. But in other words, big thing, V-shaped, and they're cutting down. Erosion is their big thing. Okay, and this is what a youthful stream typically looks like. In of course, this is just a kind of a youthful drawing, right? But you can see nice V-shape, steep sides, steep slopes, river at the bottom. How this happens, if you see that blue line, that's representing the downcutting river, that thick blue line in the middle, vertical line. And as that river cuts down, the yellow part is the land that sloughs off into the river. So as the river cuts down, you can imagine that the sides are over steepened on the ground around it, right? So then they fall in the river, and the river carries the material away. And then that, as the river keeps cutting down, more material falls in and is eroded away, and you get these V-shaped valleys. The other type is the mature stream, okay? So we have a youthful stream. In the life cycle of a stream, there's also mature streams. These are usually found near the mouths of rivers. And in mature streams, whereas in youthful streams, erosion is the primary thing going on, in mature streams, deposition is the primary thing going on. Because why? Gradient and velocity have decreased. The valleys whereas we have V-shaped valleys in youthful streams, mature or old streams have wide river valleys with meandering streams in them that meander side to side. And the reason streams meander, because in youthful streams, streams are pretty straight. But in an old stream or mature stream, they meander left to right. And the reason is because you're getting near base level in a mature or old stream when you're downstream near the mouth of a river. And so erosion can't happen vertically anymore because we're getting near base level. So what happens? It happens left to right. Now, again, deposition is the primary thing, but there is still some erosion going on. But that erosion can't go down. It's got to go side to side. And so meanders are what form. When we look at the meander of a river, we typically have two things. When we look at a bend in a river, we have a cut bank and a point bar. The cut bank is simply the outside curve of a meander bend where erosion is occurring, and the point bar is the inside curve of a meander bend where deposition is occurring. As the stream swings out wide, its velocity increases towards the outside of the turn, decreases toward the inside of the turn. So inside we get deposition, outside we get erosion. You'll hear the term oxbow lakes. Oxbows or oxbow lakes can form where meanders are cut off during an erosion. I'll show you how that happens here in a slide or so. So here's what a youthful, as you can see at the top there, mature river valleys, wide. And then we look down at the bottom view there, looking down from the sky. You can see lots of meanders in the stream because we're in a mature stage. This is an example of a meander. You can see if you follow that center line of the stream, the line connecting deepest points in the stream channel, see that labeled there? Notice how that line swings out to the outside of the meander curve each time. And notice then in the diagrams to the right that the highest velocity area swings out with it. So that highest velocity area swings out, which encourages erosion on the outside of the bends and deposition on the inside. Remember I told you about an oxbow lake? This is how it forms. Notice how at the top diagram, the bend at the top and the bottom, see how those bends with the red erosion, the red area is indicating erosion. Notice that as the water enters the bend at the top and exits the bend at the bottom, notice that that first curve and the last curve, those erosional areas are eroding towards one another. So when we get to the second diagram, notice how those bends have moved towards one another. And then we get to the third diagram down, notice that those bends have actually contacted one another, and now the stream stops flowing around the bend and starts flowing straight because water wants to go the path of least resistance, right? So it starts moving straight. and goes on through, then thereby cutting off that meander, which then, if it retains its water, is called an oxbow lake. Just a beautiful picture of the gates of the Arctic in Alaska. You can see it's a pretty mature river valley, lots of meanders. You can see the point bars there where the deposition's occurring. You can see the cut banks. It's just a beautiful, beautiful picture. So when it comes to flooding, all rivers flood periodically. All of them do. And flooding is the result of high rates of deposition along the sides and the flanks of a river. Flooding results in high rates of deposition along the sides and flanks of a river. Okay, so imagine the water's in the channel of a stream or a river, and it's flowing pretty fast because the flooding stages occurring. But then it goes up over the edge of the river channel and flows out into the river valley. Well, that velocity of that water is going to decrease immediately when it leaves that channel, right? And when it does that, it's going to deposit a lot of its stuff. And what happens is it deposits, and I'll show you a picture in a minute, but it deposits right along the edge of the river channel, because that's where the velocity decreases immediately, and so stuff's dumped right there, creating what we call levees. These are natural levees, not levees that are built by man, but natural levees. They're usually composed of coarser material like sands and higher, as you can imagine. So let me show you a picture. Okay, so see at the bottom of this diagram here, see those levees? That's where it's labeled natural levees. Those banks that form right next to the river channel, those are formed during flood stages, like at the top. That's a flood stage at the top. When that water goes out of the channel, floods out into the plain, it immediately loses velocity and dumps a lot of its material right there on the edge. So that's how natural levees form. Okay, flat valley floors flanking rivers and levees are known as floodplains. They're formed during floods, and they compose mainly of silts and clays, typically, and lots of organic rich material. So floodplains are typically good for agriculture. All right. Again, another picture before a flood. Top flood comes over, you get the deposition of those of sediments on the other side of the channel. They build up, forming natural levees over time. Deltas, y'all have heard of deltas before. Deltas are just triangular fan-shaped deposits found at the mouths of rivers. And the reason they're there is because the water exits the mouth of the stream channel into the larger body of water, and its velocity suddenly decreases, right? And so the competence and capacity of the water decrease. So it can't hold as much stuff, and it can't hold as large materials. So then deposition happens right there at the mouth of the river, and forms new land over time. Those deltas can breach the surface of the water and form new land, and then the rivers kind of branch off and diverge into branches along the deltas. This is a Landsat satellite photo of a delta, the Lena Delta in Russia, and you can see the river mouth is towards the bottom of this picture, and then those what look like veins going out into the larger body of water. Those are distributaries. Those are the diverging stream channels as they go across the delta. Okay, so let's talk about groundwater. This would have been the second lecture, but we're going to go ahead and jump right into it. I know this is a lot of stuff. Please just hang in there, okay? We're going to get it. We're going to get it. So what is groundwater? Water contained beneath the Earth's surface, right? I mean, that's simply what groundwater is. It's underneath the surface of the Earth, and it's groundwater. And groundwater is contained in pores in the open spaces of the soil and rock, these tiny interstitial spaces. A lot of people think that groundwater is in these big reservoirs underground, like big lakes and stuff, and that's just not the case, okay? Groundwater is just contained in the small spaces and pores in between soil and rock. When we talk about these soil and rock that groundwater is contained in, we'll oftentimes talk about porosity and permeability. Porosity is just the combined volume of the open spaces in the soil or rock. The pore spaces, the fractures, how much air space is in there. Igneous rocks typically have a low porosity. Sandstone, a lot of sedimentary rocks have a much higher porosity, have a lot of space in there. Then you've got the matter of permeability, and permeability is a little bit different. Permeability is not necessarily, it's oftentimes related to porosity, but permeability, technically, the definition is it's the ability of a rock to transmit fluid. All right, it's really not so much a measurement of the amount of space in a rock, but the interconnectedness of those open spaces. Okay, so porosity and permeability are related. For the most part, rocks with a high porosity are going to have a high permeability, but not always, because they're two different things. Porosity is the number of spaces. Permeability is how interconnected those spaces are. So, for example, clays typically have a high porosity. They have a lot of space, but those pore spaces are not connected very well. So typically clays have a low permeability. So they are the exception to the rule, and they demonstrate how these two things are different. Okay. If rocks have a high permeability, we call them aquifers. And if rocks have a low permeability, they don't transmit water very well, we call them aquitards. You've heard the term water table before. Water table is the level of the underground water surface. I'm going to show you a diagram in here in a second. But there's two different zones. There's the zone of aeration, or the unsaturated zone. This is the zone that contains both water and air above the water table. And then there's the zone of saturation, or the saturated zone. And this is the area below the water table that has no air, only water that fills the pore spaces. The boundary between those two zones, the zone of aeration and the zone of saturation, is known as the water table. So this is what the water table looks like. You'll see the unsaturated zone there in the gray, the saturated zone in the blue, and the water table is the dashed blue line that separates the two. Okay. Terms that are surrounded, that relate to groundwater. Springs. Springs are just places where the water table intersects the Earth's surface, and the water will naturally flow out of the Earth from a spring. You also have regional water tables, which are macro water tables in an area. They roughly follow the contour of the land. So if you were to dig down to the water table in an area, it would typically follow the contours of the land. I'll show you a picture of that in a second. But you also have perched or hanging water tables, and these are isolated local water tables that are above the regional water table. They're usually created when an aquitard, a layer of impermeable rock, is above the regional water table that inhibits the downward flow of water. So let me show you an example of all this. So you'll see here, notice that regional water table is the one at the bottom there, and notice how it roughly follows the contours of the land there. See that? But then you have the perched water table above that, where you have that aquiclude, which is another word for aquitard, that prevents the water from going straight down to the main regional water table. And so it creates this little perched water table up there. Perched makes sense, doesn't it? And then you see the spring is where the water table intersects the land. So there it is, a graphic representation of everything we've talked about. Talking about groundwater, we got to talk about wells. Wells are simply holes drilled into the ground where we access water below the water table. All right, so we all know what a well looks like. We've all probably had some experience with a well. Again, still looking at terms. An unconfined aquifer is when water flows down under the force of gravity and fills an aquifer. Wells drilled into these aquifers fill to the level of the water table. The water is pumped from these wells, and we can create a cone of depression, which I'll talk about in a minute. A confined aquifer is different than an unconfined. A confined aquifer, the aquifer is confined above and below by an aquitard or an aquiclude. So the water fills the aquifer by flowing down into the aquifer from upland sources. This can create what are called artesian wells, which are wells where the water rises above the water table because of the extreme pressure. So you're like, what in the world is he talking about? Let me show you. All right, these are wells, right? And different types of ways of digging a well. You can dig a well, you can drive a well, or you can drill a well. We all maybe know this. But anyway, you're digging down to get below the water table so that you can access the water below the ground. All right. Well, let me talk about the cone of depression right now real briefly. This is a well. And notice how the well is sucking water out from the water table, right? Notice the little cone, the depression that's right around the well. That drawdown is because the water, right? You're pulling water out faster than it can fill back in, because water moves underground very, very slowly, okay? So if you pull water out, it's going to take a little while for it to fill back in. If you're pulling water out faster than it can fill back in, you can create a cone of depression. Most wells are going to have some kind of a cone of depression. But if you're drawing out water way faster than it can fill in, you can actually dry the well up by sucking the water away. So that can be a problem. Okay, so let me show you what we're talking about by confined and unconfined aquifers. So if you see the water above, well, that's fresh water. Actually, this only shows unconfined aquifers. So see the, look at the upper Floridian aquifer, okay? You see the one right there in the middle? Or you could, yeah, you see it. Upper Floridian aquifer. Notice how above that aquifer you have a confining layer, an aquitard or an aquiclude, and below is the upper confining unit. And then below it, the middle semi-confining unit is an aquiclude or an aquitard as well. So that aquifer is contained between two rocks that won't let water pass through. So the only way water can get in there, because it's not going to fall straight down through that upper confining unit, it can't get through that. So the only way it can get through is to go back uphill. See uphill where the black arrows are showing the water coming downhill? So it comes in through the sources in the upper areas of upland area. And it flows down all the way downhill through that aquifer until it gets down to, about halfway down the page. Now, you can imagine that water, it's like being in a pipe. It's under a lot of pressure, right? So when you dig a well down into that upper Floridian aquifer, now all of a sudden you've released the pressure. And so the water doesn't just pool there. It actually flows up and out, just like you're seeing there in the diagram. See, it says water level about 65 feet above the land surface. In other words, that water flows out. It says flowing well there. Flows out. We call that an artesian well. Okay? An unconfined aquifer would be like if you took the upper confining unit away and the water could flow straight down into the upper Floridian aquifer, which means if it was unconfined, then we wouldn't have the artesian well situation. Okay. Again, we're still learning terms. Hot springs are when heated water rises to the surface. We used to not know how water was heated in places like here in Virginia. Geologists just assumed that if heated water was coming out of the ground, then it must be a magma source underground somewhere to heat that water. We've since found that some scientists at Virginia Tech determined that actually, if water descends into the crust far enough, it can heat up, right? Through the geothermal gradient, and then that water can come back up because heated water rises through cracks and stuff in the surface, in the crust of the earth, and spill back out. In places like Hot Springs and Warm Springs, Virginia, that's exactly what's happening. It's called meteoric circulation. The water goes down deep into the Earth's crust through cracks in the Earth's crust, and then comes back up through cracks in the Earth's crust as warmed water. Pretty cool. Fumaroles are steam released from ground under superheated groundwater. Now, fumaroles are typically formed around magma sources, and so hot that it's steam water, and you can see this is steam coming up out of the ground. It looks kind of wild. You oftentimes see these around active volcanoes and things like that. Geysers, again, are typically found around magma sources because this water is extremely hot. These are explosive eruptions of heated groundwater from the earth. And typically how this works is that the chamber of water underneath will be heated by magma. The water superheats and then flashes to a gas at some point. Then it rises rapidly up to the surface through some conduit and then spills out onto the surface for a few seconds or 30 seconds or a minute or whatever. And then when all that water or a lot of that water is evacuated from the underground reservoir, the geyser ceases, the water heats up again, it flashes again, and the process is repeated. Old Faithful in Yellowstone National Park is probably the most famous example of this in the world. When you're talking about groundwater, you'll hear this term, Karst Geology. Karst just simply means cave. That's all it means. And a cave's obviously just an underground space in the rock. Caves form in easily dissolved rocks, and the groundwater will sit in there and it will dissolve a rock. And then later, when the groundwater table drops, it'll expose an open area in the rock. So that's what bullet number 4 is about. Groundwater dissolves rock, and then when the groundwater table drops, open spaces are exposed in the zone of aeration. A sinkhole is just simply when one of these caves underground collapses and leaves a depression at the surface of the earth. This is an example of a sinkhole. This is in Florida. Picture taken from the Florida Geological Survey. So somewhere down in there was a cave, and the top of it collapsed, and that's what we see at the surface. We're looking at cave structures. A lot of people like this kind of stuff. Speleothems are just another way of saying cave structures. They form as groundwater drips into a cave. We call that dripstone. They form as carbonate rock deposited through evaporation, so the water evaporates, leaving behind the calcium carbonate deposits that form the speleothems. There's three basic types. There's stalactites, stalagmites, and columns. And for some reason, I just lost. All right, there we go. We're back. Not sure what that was about. Hold on for 1 second. Just getting myself settled. All right, so stalactites, the C, C, you can think about a ceiling. That's a spire that hangs from the ceiling of a cave. A stalagmite, G for ground, is a spire rising from the floor of the cave, and a column is when the stalactite and the stalagmite connect with one another over time and form a column from the top to the bottom of the cave. A stalactite, water drips, and as it's dripping, it deposits material at the ceiling of the cave, creating these spires. When the water droplet drops to the bottom and lands at the bottom of the cave, it evaporates, leaving behind a small deposit of calcium carbonate, forming over time these stalagmites. Here's a dramatic example of these. You can see them all labeled there, some columns and stalagmites and stalactites. When we talk about groundwater, we got to talk about environmental concerns, because groundwater is streams are easily polluted. And if you're polluting streams, you're polluting groundwater. All right? Because streams and groundwater are very much connected. If you pollute one, you pollute the other. So pollution affects streams, pollution affects groundwater. We need to be very careful. So throwing things into the streams, throwing things on the ground, oil onto the ground and into sinkholes and things, is a recipe for environmental disaster. Okay, so we've got to be very, very careful, because it's easy to pollute our streams and our groundwater. Saltwater intrusion is an environmental concern. Near the ocean, where streams and groundwater table are near the ocean, sometimes the ocean can kind of back up into the groundwater. And if we're drawing a lot of groundwater out through wells, you can actually start to suck up some of the salt water, and I'll show you a picture in a minute, into your wells, and you can actually pollute your groundwater table. So you got to be very careful with wells near the ocean. And then, of course, overuse of groundwater, excessive cones of depression, we talked about a little bit ago, can result in the abandonment of wells and the using up of water resources that can be detrimental to the environment. Right? So, as you can see, this shows how groundwater and streams and lakes and whatnot are related. See how the groundwater flows right into the lakes and the streams. So if you pollute one, you pollute the other. This is a saltwater intrusion. Notice how you've got the freshwater there and the saltwater, and how they have a zone of dispersion. If you put a well, say, on the land surface to the left and started to suck up too much of that freshwater, you can start to suck in some of that saltwater, and it can intrude into the freshwater and pollute it. So you got to be careful. And this is just demonstrating how you can overuse groundwater through the use of wells. These two houses, A and B, are drawing a lot of water, and they're drawing down, in the bottom diagram, they're drawing down those cones of depression to dangerous levels where these wells could be abandoned at some point. And, that'd be bad. All right, so that's the lecture. Again, just do everything I ask you to do in the email for this week. Hang in there. I know this is a lot of information. I know you'd probably rather be in a lecture where we could talk and you could ask questions, but you can still ask questions. You just got to call me, email me, whatever. I'm here to help you any way I can. All right. Have a great day. I will talk to you soon.